Over the next few videos, I want to take a look at some more relationships between systems of linear equations and invertible matrices, sort of using info that we can get from systems to tell us about the matrices, and vice versa, stuff we might know about matrices to help us learn a little more about systems. So here's the first thing. We have a theorem here that says a system of linear equations has either 0, 1, or infinitely many solutions. I mean, we may have sort of implicitly felt this or known this for quite some time, that you never end up with two solutions to a linear system. You have 0, 1, or infinitely many. So let's actually prove that at this point. So the proof looks like this. It starts off kind of in a funny way. I mean, isn't it obvious? Obviously, there is either 0, 1, or more than one solution. So really all we have to do is to say, well, suppose there's more than one solution, and show that there has to be infinitely many. Okay. So suppose that there's more than one solution. Now, if there's more than one solution, then there's at least two, right? So let's let x1 and x2 be solutions to, and we haven't actually stated what the linear system is yet, so I'm going to do it right now, to the solution ax equals b, right? Where A is an m by n matrix, so A is m by n matrix, n is a column matrix, n by 1, and B is a column matrix, m by 1. Okay, this doesn't necessarily have to be square matrix. It could be, but it doesn't have to be. So the thing is, no matter how many equations and how many variables, we're claiming that there's either 0, 1, or infinitely many. So I'm assuming I've got two solutions to this system. So that means A times x1 equals b, and A times x2 equals b. So now, again, these little hats just sort of indicate that I've got a column vector, or column matrix, whatever you want to call it. Let's look at this now. Let x0 equal x1 minus x2. Right? So these two column matrices, I'm just going to subtract them to get this one that I'm calling x0. Now I want to take a look at some properties of x0. Now notice that A times x0 equals A times x1 minus x2 equals, actually I want to write that down here, A times x1 minus A times x2, but A times x1 is b, because that's what we had up here, and likewise A times x2 is also equal to b, because x2 was a solution of that system. So b minus b is equal to 0. Okay. What I've shown here is that if I have two solutions to the system and I subtract them, what I end up with is actually a solution to the homogeneous system with the same coefficients. So rather than ax equals b, I have ax equals 0. Okay. Now I'm going to use this x0 to generate infinitely many solutions to my original system. All right. Now look at x equals x0 No, what am I going to do? X1 plus t times x0, where t is any real number. Right? So there's infinitely many different choices you might use for t right there. Take a look at ax. Well, if x is equal to this, then you're looking at a times x1 plus tx0, which, remember, these are matrices now. This is a m by n. This is a column matrix. This is a column matrix times a real number t. When I multiply this in, I've got, so there's a distributive property, a times x1 plus a times tx0. There's a property that allows me to take this t out in front there, so a times x1 plus t times ax0. Now remember, x1 was a solution to the system ax equals b, so ax1 is actually equal to b. x0, on the other hand, was a solution to a homogeneous system, so ax0 is actually equal to 0. So this is b b plus t times 0, but t times 0 is just 0. So this is just b. So what we have is a times x, where x looks like this, is equal to b. So for every value of t, we have a solution to the equation to the system ax equals b. Hence, infinitely many solutions. Now, graphically, I mean, what did we do as a picture? In a way, you know, when you're thinking, oh, what did I just do? Did I just subtract, just get rid of my equal sign? Yeah. When you're thinking about a system of equations, you know, the simplest sort of system of equation you might have is a single equation in two variables. So maybe something like ax plus by equals c. You know, we know that the graph of that thing is a line. I mean, I hope we know that. So what did we do? We took 2 points on the line and we subtracted them. Now, we'll see this in more depth later, but really what we did is we found this, you think of them as vectors, as a vector that points from here to there, and the subtracting of the two really gave us that. And so then we said, okay, now take this x1, this first point, and add on multiples of this thing. So you add on small multiples, or you add on bigger multiples, or you add on even bigger multiples. And what you're doing is you're describing the whole line of points that contained x1 and x2. And that this x1 plus tx0 is a way of describing all the points along the line. So essentially what we do is we say, well, if there's two solutions to the system of equations, then the line that contains those two solutions, every single point on that line is also a solution to that system. Okay. So this is a pretty basic theorem that we have. Systems of linear equations have either 0, 1, or infinitely many solutions.